Any chance you guys can hear me?
Yes, I can hear you.
Oh, good. Okay, my computer is telling me that I'm not, it isn't working. All right, I apologize for the delay in opening up this morning. I'm having some technical difficulties here at home. Look, my wife painted my office yesterday, so it all looks better. It does mean that now I have to get all the settings right on the computer, so I'm a little behind. All right. Well, let me just dive in and ask if you guys have questions that you need me to address. You have a homework set that's due tonight, and the material that's on that will be part of what's going to be on the exam on Friday. So I want to make sure everyone's comfortable with the material. I do have, I've already got slides prepared actually for line integrals, because I know that's the topic that we have really just started the other day. But apart from the line integral material, do you have questions that you want to ask me? No? Nobody?
Can you kind of go through how would the exam proceed?
Oh, good question. So, yeah, I tried to write an exam that would be a lot like one that I would ordinarily have given you if we were live and in person. So a bunch of quest type problems and then a couple of free response questions. So here's what I've done. If I've understood the instructions correctly, I can set it up so that you have a fixed amount of time to work on the quest problems, but you can start them whenever you want within the time window that I give you. So what I'd like to do is to set it up so that the clock will start sometime on Thursday, and then by the corresponding time, 24 hours later, sometime in that 24-hour window, you're going to have to work on the quest questions. And I guess I'll give you like 2 hours to work on them at a time of your choosing. Okay, so give yourself a block of time so that you can work on it slowly and carefully. And then in addition, there will be 2 free response questions. I'll just write them up, like a test looking page, and I'll put links to it on the course syllabus page and on the Canvas page. And I'll give you a URL by email. So during those same 24 hours, you'll be able to work on those free response questions. Now, what you guys are going to have to do is to leave yourself some time before the time limit is up, because you're going to have to somehow scan your answers, unless you just want to like type them out on the computer in the first place, because you have to somehow get that back to me. Now, there's a place on the Canvas page for the course that's called assignments, and I'll have a blank space there where it will be waiting for you to upload your scanned answers. If you have trouble making that work, you can also just email me your responses to those 2 questions. So I'll try to set it up today. Actually, I'll put like a little practice spot, so you can try playing around with the Canvas thing and see if you can get the scanning and the updating to work. I mean, there's apps you can have on your smartphone that'll let you kind of swipe your camera across the image and it will reconstruct a PDF for you. If it comes to that, you could also just take a photo, send me a JPEG, and I'll try to make that work. But that's the structure of the exam. I know it's a lot more complicated for you guys to get it and send it back to me, but the exam itself is just going to be the multiple choice type quest questions that'll actually be done through Quest, like a homework, and then the free response questions that you'll have to figure out a way to get back to me. Does that answer the question? Or Malik, you have your hand up too?
Yeah, I mean, I was just wondering, so for the free response, will we have the full 24-hour window?
Yes. For that, you have 24 hours. So I would encourage you to read the questions at the start of the period, and then that gives you a chance to just think about them. So, I mean, this is what I do when I'm trying to do some math, right? Is you read a question and then that's when you go have dinner and you take a shower and whatever. And the problem can sort of be percolating in your brain for an hour or two. And then you sit down and you try to work on it for a little while. And then I would advise you to give yourself a block of time that's sort of well in advance of the time when it has to be finished, just to make sure you don't run into a time pressure. Sit down and do the quest problems, and then finish working on the free response. So, I mean, do it in any order you like, but just we're trying to be accommodating here during this period of lockdown. Just I know some of you are on different time zones and things, but just to figure out a way to leave yourself time to work on it. So it's all this stuff will be available to you midday tomorrow, Thursday, and then it'll be due midday on Friday. Oh, and that means Friday we won't have a class because you'll be finishing it, I'm sure.
So,
Okay.
but
I
I just had a question in regards to the quest. So the quest will be a 2-hour window. We have 2 hours. So we start the quest portion of the exam, and then we're just given a 2-hour limit.
Correct.
Automatically submit whatever we have.
Correct. At least that's my intention. And I have the people from Quest, they're telling me how I'm supposed to do this. So we'll see if I can follow their instructions and make everything work right. I mean, as with everything else this semester, guys, I just have to ask you to be cooperating. We're all doing our best here. And the technology never seems to quite work the way it's supposed to, but we'll try to make it work. Brianna, you have your hand up.
Yes, I have 2 questions. So one, would you be able to send an email detailing all of this, like either through Quest or Canvas, just so that way we all know what's going on?
That's a good idea.
Then, could we also just, I guess, review like the most important things like today, because it has been like a while since some of the things that we have covered, like we actually tested on, or like we've actually practiced. So.
Yeah, good point. Yeah, so let me address that. The intent is for this exam to cover everything since the last exam. So the last exam was right around the time that we were working on vector fields, and I'm pretty sure I did not give you guys questions about the vector fields themselves on the last exam. So you should review the definitions of the divergence and curl and gradient. And when I say review, you got to know the definitions and how to compute them. And then there's a few theorems that were in there they're in there to make your life easier. They tell you, for example, that when you take the curl of the vector field, then you get 0 and something else is equal to 0, that kind of thing. And you may recall there was also a whole page worth of formulas that amount to basically a product rule for all those different types of derivatives. Now, I'm not going to try to police this exam, so I'm just going to consider that it's open book. So you don't have to try to memorize those formulas. Just know where they are in the book and know how to use them when they show up for you. Then, after the vector fields, that's when we started talking about integration. And everything has been different types of integration and methods of calculating these integrals and so on. But in spirit, they've all been the same. I give you a set and a function defined on that set, and then you chop up the set and evaluate functions and so on. I've said the same thing many times. So I would like you to feel comfortable understanding why an integral might be the right thing for you to start computing if I'm asking you for a mass, or if I'm asking you for an area. Those can be computed in terms of an integral just because of what an integral measures. But then I know you guys are concerned about how exactly to calculate the integrals, and so you should be familiar with Fubini's theorem. You should be familiar with the change of variable theorem, setting up the limits of integration and so on. And now we've talked about integrals over curves, the path integrals, I mean, and integrals over surfaces. And both of those categories require the parameterizations that we've been dealing with. And then the final topic is this idea of line integrals. I think that's section 7.2. It's again, path integrals. It's just that the setting up of the integral involves a vector field somehow. We'll talk about that today. And I think those are all the topics that I would put on the exam. Those are all the things we've done since the last exam, and it's a lot. Am I forgetting something? Is there something else that you were going to say? Will this be on the test?
No, I just wanted to see all the content. Thank you.
Yep, that's it.
Could you also like send that in the email, just like write it out generally?
Sure.
Thank you.
I mean, the good thing from your point of view, guys, is that we actually have been following the book pretty carefully. There's only been a couple of sections that we skipped over. And, you know, in the beginning of the semester, I deviated from the book just to set up a lot of the groundwork for the geometry. And you've been seeing it now, all the stuff about parameterizing curves and surfaces. But, you know, pretty much we've just been going section by section like in the syllabus. All right, those are all good questions. Any others about the exam? Hey, and let me just stress again, you guys don't need to be getting too like nervous about this exam, because remember, grades are kind of loose this semester. If you guys end up at the end of the semester with a grade you don't like, you can always change the course to pass fail after the semester is over. So don't stress out. Just do your best. All right, let me turn to the content then. So this most recent homework, it's giving you some questions about path integrals and surface integrals. And just as a reminder, both of those things you should recognize that it's one of those two categories, because you should see a real valued function floating around somewhere. And by that I mean there should be some function, something written out with x, y's, and z's, but it's a function that returns a single number at each point. There should be no references to vectors or dot products, and basically nothing appearing in boldface. So that's what the path integrals and the surface integrals are. And of course, to distinguish those two from each other, what you should be just noticing is whether or not the region that you're integrating over is some kind of a curve, a one-dimensional set, or some kind of a surface, a two-dimensional set. So questions or comments on that? Okay. Then the other thing that you did see on this homework set is suddenly there do appear vector fields on some of the questions, and you recognize those in part because there's a big black dot right in the middle that's intended as a dot product, or you see some stuff in boldface, and the boldface again is intended to be an indication of a vector. So that's the material that I know is newest, and I wanted to go over that today. Malik, you have your hand up.
Yeah, sorry. I was confused actually on the formula for the surface integral, because in the book it says that it's a function times phi, or a function of phi, then times the determinant of the cross product of t with respect to u and t with respect to v. And I was just confused why they had t and like what the t refers to and what the phi refers to.
Actually, they shouldn't both be in the same formula. The t's and the ph's are, let me pull out the book. Those are both letters.
It's on page 393. It says f of phi of u of v times the determinant of t sub u cross t sub v. I was just confused like why they made the difference between t and v.
Okay, so first of all, it's not a determinant. The double bars there are just asking you for the magnitude of a vector.
Okay, sorry about that.
And you are correct. I have used this book for years, and I never noticed that that's actually a kind of a typo. I mean, both the phi and the t are just the names that he uses kind of interchangeably for the functions that are parameterizing the surface. And I don't really know why he goes back and forth between the two. but he actually messed up. This formula, you should use one letter for where both of those occur. So both the phi and the capital T are supposed to be referring to the parameterization function. I don't really know why that is written that way. Maybe he intended the capital T to stand for tangent vector because they will be tangent vectors. Yeah, I guess he was consistent about that. But no, from your point of view, don't try to worry about what they stand for. Those are both just the same thing. So in both of those cases, here, let me swing the camera out so you guys can see what he's talking about. This is the, Malik, correct me if I'm wrong, but this is the formula you were referring to. Oh, you guys, that's a lousy focus.
Quality's kind of bad.
Yeah, sorry.
It's
well,
on 393 though.
Yeah, so if you, any of you guys, if you do have the book, it's here. I'm on the top of, well, it's page 393, and he's talking about integrals of scalar functions. So again, scalar means it's just spitting out real numbers at each point, and the function is defined on a surface. So the quantity, I know you can't read this here, but what shows up on the left is just one of the forms of notation for, please compute the integral of the function f over the surface S. Same exact interpretation that we've used every single time. You're going to chop up the surface into pieces, evaluate the function, multiply the size of each piece times the value of the function. Okay, and then what's on the third formula, after the equal sign, that is really bad, out of focus. That third formula right there says to do what I have been telling you to do, which is you come up with a parameterization, and that's what he's calling capital phi. And then you change three things in the original integral. You change your region of integration. Instead of being a surface in three-dimensional space, it changes to some subset of the UV domain. So that's the first thing you change. You figure out the U's and the V's that go with your surface. The second thing is you have to change the original integrand, but all you're doing there is you're substituting in your formulas for X, Y, and Z. Each one of those will be expressed in terms of U and V. And then finally, you have to rewrite this differential. We have to take into account how the areas are being stretched. And as I discussed, I think it was last Friday, that can be computed with taking the magnitude of the cross product of those two derivative vectors, the two columns of the derivative of the function capital phi. So he's mixing the letters phi and t in one formula, and I don't really know why, because that's not necessary. So first, Malik, does that answer your question? Phi and t are the same thing.
Yeah, okay. I was just confused on that. That clears it up.
No, that's fine. And so for anybody else, is there anything else that I should be saying about the surface integrals? All right, good. So you know how to integrate scalar valued functions on paths, and you know how to integrate them on surfaces as well. And now the question is, what the heck are these line integrals? So let's talk about those a little bit. So it's going to be the same kind of thing ultimately as we have been discussing in the past. Somebody's going to give you a path in space, and they're going to give you some function defined on that space, and they want you to compute the integral. And you're going to chop the path up into little bits and so on and so forth. Okay, but specifically, how do the functions arise, the functions that you're trying to integrate? And the answer is that sometimes, in addition to the path, you have a vector field floating around. And I gave you an example last time thinking about wind that you have to fight as you walk along a path or something. So this kind of a setting of a problem will always involve a vector field that will have to be given to you in some kind of explicit way. So you'll see little formulas that express a vector at each point xy or xyz. So you'll have multiple components to this function f. And in the presence of such a vector field, then the kind of quantity that will lead to an integral is somebody might say, yeah, you know what, I would like you to walk along this path and measure the size of each one of these pieces, but multiply them by this expression that's talking about the contribution of f as you walk past a little portion of the curve. And this is the kind of formula you would have seen in a physics class, that you look at the magnitude of the force or whatever the vector field is, but that magnitude gets reduced by a factor of a cosine of theta, where theta is the angle between the direction that you're moving and the direction that the force is pushing you. So in the case where you're moving directly in the direction that the vector field is pointing, well, then this is just the magnitude of the force. So you're multiplying the magnitude of a force times the distance that you're traveling. Force times distance is work. Without a minus sign in here, this is the work that the vector field, the force field, is doing on you. It's the opposite of what you have to do if you're trying to fight the force. This presence of a cosine, though, it tells you that if, for example, the wind or the force is blowing directly perpendicular to the path, then there's no work being done. That it's kind of irrelevant to you that the vector field is flowing perpendicular to where you are. So it's a natural kind of thing to have to compute in some of these physics type problems. And it can be computed just the way I've described it, although you know that you can also represent this kind of a quantity in terms of dot products, and I'll show that in a second. If you realize from the kind of science point of view, the physics point of view, that this quantity might be worth computing, then you should say to yourself, oh, well, that's just a path integral the way we've been setting them up. The region of integration is exactly the curve that you're following. The way you're measuring sizes is with bits of length. And the quantity that you're adding up all the time is just this one. So it's nothing different from any of the other path integrals that we've been computing. But as it turns out, it can be actually easier to compute them despite the fact that this formula looks kind of messier. So here's how I'm going to make it look nicer for you. This thing that I need to evaluate at each point on the curve, you're supposed to be, well, you write down the vector field, and that's a vector at each point x, y, z. You got to take the magnitude of that vector. You multiply by this cosine, and it sounds like a horrible job. But you know that you can recompute such a product with cosines in it by taking a dot product. This extra factor of a dot product is what you would get of a cosine, would show up if you were to dot the vector field with a unit vector that points in the direction that you're moving on the curve. Now I say unit vector because you may remember from early in the semester when we computed the size of a dot product, that was given as the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between them. So you kind of need that to be a unit vector. If you want, you could use a non-unit vector, but then this dot product would be off by this extra factor of the magnitude of v. So just divide by that magnitude. So now at least there's no trigonometry involved, and this gives you a way of writing the same integrand in terms of the vector field that was given, and in terms of any vectors that you can find that are always pointing tangent to your curve at each point along the curve. Now, we're going to have a usual technique for how we compute those tangent vectors in a minute, but I'm going to give you a more geometric example first. So let me give you an example of a vector field. This is just in the plane now. I could do stuff in three-dimensional space, but here's a vector field in the plane. At each point x, y, you get a vector. And here I've drawn a few of the vectors that you would encounter at different points in space.
Excuse me, Dr. Rusin?
Go ahead.
Could you turn off the light to your left?
I thought it would make things better. Is it making it worse?
Yeah, right there. That's perfect. Thank you.
It's
Sorry,
better now, huh?
it was just bad glare for me.
Okay. Yeah, that is better, isn't it? All right. So I've evaluated this vector field at a few select points, and I've also shown you a path, and the thinking is I'm going to walk around this path and create just that kind of a sum. At every point, I'll be adding in a dot product. You know, it's the size of this vector field that you see right there, but I'll reduce it by the cosine of the angle that there is between the vector and my path. So according to what I had on the previous page, what I need to do is to figure out some vector that's tangent to the curve. Well, look, I've chosen to take a semicircle here as my path. And I did that because I actually know a way to get a vector that's tangent to the curve. If you're on a circle and you draw the vector that goes straight from the origin to the point that you're standing in, well, that vector is going to be perpendicular to the curve, right? That's kind of what makes a circle be a circle, is that all the vectors that go from the origin to any point that's on the circle, that vector is always perpendicular to the direction vector on the circle. So, well, of course, that vector, if you're at the point x comma y, the vector that joins you to the origin is the vector x comma y. So there's an example of a vector that's perpendicular to your curve. So if you want a vector that's tangent, just, if you flip those two components around and throw in a minus sign, now you'll have two vectors that are perpendicular to each other. The dot product is 0. And so that tells you that at each point x comma y on the circle, you can use this vector right here, this v, as to represent a vector that's tangent to the circle. And so I can now return to the previous formula and say, oh, well, if you wanted to reduce the vector field by a cosine, just compute this dot product. And here I go. I take the vector field, I take the dot product with my chosen tangent vector, and then I remember I'm supposed to have a unit tangent vector, so I divide by its magnitude, which you know is the square root of x squared plus y squared. And I computed the dot product, I multiplied everything out, and I simplify it a little bit. I can simplify the denominator too, because I said I'm staying on a circle. I don't know if you noticed, but this is a circle of radius 2. So all the points that are actually on the circle, that denominator will be a 2. So here's the point. I had a pretty geometric looking path to follow. It was such a simple curve that I had a way of calculating a tangent vector at each point. I had a formula that told me what vector might be pointing along the curve no matter where I stood. And then I was able to compute this dot product and simplify it, and I now have a scalar valued function, a real valued function at each point x comma y, and that's the quantity that I need to integrate on the path. So the thing that I was describing earlier as being this strange looking integral with dot products involved, I've just done the computations to simplify it into one of our path integrals. I just have an explicit path in front of me, and there's an explicit formula of x's and y's that I need to integrate. And you know how you do it. I won't go through all the steps now, but you would have to find a parameterization of the curve and substitute in the x's and y's, find out the range of t's that you need. Don't forget to put in the speed, the absolute value of the derivative of your parameterization function. That's the little fudge factor that goes in. So at this point, everything is just like all the other path integrals that we've done. And so all I've done is I've shown you how these new kinds of integrals that start from a vector field somehow, how they turn into a path integral like we've been doing. Now, there's one thing you need to be aware of. When I said I was going to find a tangent vector, what I proposed was I took my normal vector, the perpendicular vector, and I said, oh, look, I can just swap and throw in a minus sign, and this will be perpendicular, perpendicular to this one. So this is a tangent vector. I could have put the minus sign in the other spot, and I would have gotten a different vector that's also tangent. If you do that, though, when you go through the process of computing all the rest of this dot product, nothing will change in the f, nothing will change in the magnitude, but you'll have a sign difference in the top. And so you'll get exactly the negative of what I've computed over here if you use that tangent vector instead of that tangent vector. You should be asking the question of, well, which one am I supposed to use? And the answer is it will depend on the application that you had in mind in the first place. In the very beginning, when I said I was going to wander over a path and keep multiplying the lengths of the pieces by, well, the magnitude of the force but reduced by this cosine factor, you need to say, are you going to measure the angles sort of going towards the right or the angles going kind of towards the left? Because in addition to that little angle that I've called theta there, you could look at the supplementary angle, 180 minus pi, and that could be thought of also as the angle between the force field and the curve. So it's a question of, well, did you mean to be looking at that angle or this angle? And that can only come from the application. As I said when I started this one, are you trying to compute the work that the force field does on you, or the work that you have to do to fight the force? Because they'll just be opposites of each other. They'll be negatives. So it's kind of your job to make a decision as to which one of those two applies. Ordinarily, these situations arise when I'm going from one endpoint towards the other endpoint, and I'm calculating the angles between the force field and the tangent vector that points in the direction that I'm traveling. So ordinarily, in these problems that involve a vector field, you will have been told not just a path to travel on, but a direction to travel on. So you will see these two integrals written out, and they'll be almost the same. You'll be evaluating a path integral in both cases, but to distinguish whether you're going from left to right or right to left, you need to put a little arrow in there. And that's different from the other path integrals that we've had before. Nothing about the computation of the integral is different. The difference comes in the setting up of what the function is that you're integrating in the first place. Did you mean to be integrating that function or the negative of that function? And that can only really be told from the applications. All right, so that's the idea behind what these line integrals is. You start with a vector field, and for whatever reason you need to be taking the magnitude of those vectors, but reduced by a cosine of one of the two angles that the vector field makes with your path. Now, in the one example that I already started for you, I was able to get these tangent vectors from some geometry. I knew the geometry of a circle was simple. In general, it's kind of hard to get a vector that's tangent to a curve by just looking at the geometry. The way that we usually get our tangent vectors is to use the parameterization. I mean, when you go to compute the line integral, the path integral, you're going to have to parameterize the path. So go ahead and parameterize it. Think of your parameterization as being a recipe for how to walk along the curve. It'll tell you your position, what your position should be at all times t. And that's the thing we're calling phi of t. Well, if that tells you your position at all times t, then when you differentiate that, you'll get your velocity, and your velocity vector always points along the curve. It'll either point this way or this way, depending on whether you're driving that way or this way. So in either case, this is a way to get a vector that's tangent to your curve. And since I've already mentioned that it kind of makes a difference, are you going to be looking at that tangent vector or that tangent vector? That amounts to saying, when you parameterize your curve, did you mean to be parameterizing it from left to right or from right to left? It doesn't really change the value of the path of a path integral. What it changes, if you decide to go in the opposite direction, is exactly what function is it that you're integrating along the path, because the two options will be negatives of each other. So this is the thing that we're relying on now, is that if you don't have simple geometry to help you get a tangent vector, the other way, the easiest way in almost every case to get that tangent vector is to just compute your velocity as you walk along the curve. All right, so now let's think of how we would be computing our path integral using the velocity vector as our tangent vector. So remember, I was setting this all up before, where the thing we were evaluating at each point on the curve was going to be this dot product with a unit vector, or I could take a dot product with any other tangent vector as long as I divide by the magnitude. And now this is my choice of a tangent vector. So I'm putting the derivative of my parameterization function in where the other tangent vector was before. And of course, its magnitude goes down here. And that means that now I can write one of these integrals that has the big dot in the middle. I can write it as one of our more familiar path integrals. You're going to be integrating over some range of t's. This is how you compute a path integral, right? You've got your parameterization. So you change your region of integration to now be the set of t's that you need to parameterize the path. You've got to rewrite your integrand. That's the f dot u thing. F dot u, which is this, which is that. Now here you'll have a bunch of t's, but in the formula for the function, for the vector field rather, there's still x's and y's and z's, so you have to substitute those away. So you just turn all of those into functions of t as well. So there's your vector field written now as a function of t. More precisely, this is telling you what vector you will feel for the wind or the force at each moment in time. You're referring to not the position you're standing in, but the moment in time that got you there. That's that part. And then comes the rest of this. I haven't changed that part. And then finally, remember that when you are trying to actually evaluate a path integral, you change your region of integration to a bunch of t's. You change your integrand, so it's all a bunch of t's. And then you have to multiply dt by your fudge factor. Remember, this is the stretch factor that accounts for how the length of the intervals of t's has to be adjusted to get you a length of an arc on the curve. And that's how you would evaluate this path integral. I turned the line integral formula into a path integral on the previous page, and now I'm trying to evaluate the path integral. And you got to admit, it looks terrible. But magic happens, because there are two references in here to the speed. One of them came about because I had to change my tangent vector into a unit tangent vector, and so that put the speed thing in the denominator. But then the other one talked about the difference between increments of time versus increments of length, the fudge factor that I keep talking about in these parameterizations. And you know you get length by just multiplying speed times time. So the speed shows up twice, but it's once in the numerator and once in the denominator, and those two factors cancel. So actually, you never need to compute that. These integrals, these line integrals that I'm discussing now, unlike the path integrals that we've been doing, you won't have to compute any magnitudes of the derivatives. You will simply be computing the other factors. There's the vector field, or what you experience of the vector field at time t, and you take the dot product of that vector with your current velocity vector. So actually, these line integrals in practice turn out to be easier to compute than the path integrals. So let me show you another example. Oh, sorry, I wanted to get the notation down first. So, let me disentangle this here. You know how to compute a dot product. You just take the sums of the products of the x, y, and z components of that vector and that vector. So this vector field, when somebody gives it to you in the first place, they'll have to give you three separate functions of x, y, and z for the, well, should I call it the x and y and z components of the vector. Of course, if it's a vector field in the plane, there would only be two components. But if somebody gives you those three functions explicitly, then it would make sense for you to explicitly write out the three components of your function phi as well. Phi was supposed to be telling you your position at time t, and of course your position at time t has an x component and a y component and a z component. So that's three component functions. I'm calling them phi1, phi2, and phi3, and you need to differentiate all three of those. And then what you see that I've written down here is the dot product of the vector field capital F and the velocity vector. And it's so many symbols, I decided to just abbreviate it a little bit. You're integrating over a range of t's, you're integrating with respect to t, and everything that you see in here is a function of t, but it's a sum of three products, and every one of those products involves one of the components of capital F multiplied by it's the derivative of your x coordinate or your y coordinate or your z coordinate. Now, the notation that a lot of people like to use is, people like to treat these derivatives as fractions, which they're not. But in terms of the symbolism, if you think of that as a fraction, then multiplying by a dt just cancels all the denominators. And this then becomes a notation that you might see for these line integrals. People will write out the component functions of the vector field. That'll be a function of x, y, and z, and so will that, and so will that. And they will put the symbols dx after the first, dy over the second, dz after the third. It doesn't mean anything different from all the other ones. It's just a notation that tries to get you to describe what it is you need to compute. Other people use this notation. You can see that it's kind of the same as that. Other people like to say, well, duh, if you put the three components of capital F together with angle brackets, that's just the vector field capital F. And this, I don't know, it's a little displacement that has x, y, and z coordinates, so we'll think of it as a vector displacement. And so they use this notation. And I'm putting a little arrows in just for today to remind you that that would be thought of as a vector. You might see it in boldface. I might also use the letter capital L instead of S because these are changes in your position. They are lengths in space. So all of this stuff that you see here, it's not computing anything different. These are just different notations that you should expect to see. And in particular, the book and Quest both like notations like this. You can recognize that these are line integrals instead of path integrals because there's the big dot in the middle and there's vectors indicated either with arrows or with something in boldface. So get used to the varying notation and don't get scared by it. It's just asking you to compute the same line integrals that I just described earlier. So now let me show you just a generic example. So here I've got a path indicated with a direction. I want you to take that circle of radius 2 again, but to go counterclockwise. And here I've written out the two components of the vector field. So the vector field is this quantity, comma, this quantity. At each point, x, comma, y. That's the same vector field that I had for you earlier. I drew the little arrows. But this notation now is one of the notations that I indicated that people use for these line integrals. And the way you're going to compute them is what I had at the end of this page. After you get a parameterization, you simply substitute into the vector field, compute the velocity vector and the dot product, and that'll be your function of t that you have to integrate. So here I go. Here's my chosen parameterization of a circle. I hope you're not surprised. I'll need that bunch of t's to get halfway around the circle. So I'm going to integrate over that range of t's. And what I'm integrating is just going to be, well, I'll take these two components of the vector field and I'll substitute in all of this for x and all of that for y. And so you get, there's the first part, that's the x plus 2y. And the second part will be this. Oops, sorry, that much. Then you're supposed to take the dot product with your velocity vector. The velocity vector is obviously minus 2 sine of t, comma, 2 times the cosine of t. And those are the two components that you saw here. And all the rest of this with the multiplication and the addition, that's just me computing a dot product. I'm sorry that I don't know how to write this dot a little lighter, but that's just an ordinary multiplication of a number times a number. That one is not a dot product. Okay, multiply it all out, simplify a little bit, and you discover that this is the function of t that you need to integrate with respect to t between those two values of t. I leave it to you to actually work out these integrals. You might want to use your Calc 1, Calc 2 skills. I get a certain number. And this is then the value of the line integral. If you had chosen to take exactly the same vector field and integrate it with the path going the other way, that would replace those angles on the one side with the tangent vectors. You'd be replacing them with the angles on the other side. So all of the cosines would be negatives. The integral would be exactly the negative of this. You'd get 6 pi instead of negative 6 pi. So that's it. That's how you compute these line integrals. And I summarized here the different things that I've said about these line integrals. What they mean is exactly what all the other path integrals have meant, but the function you're integrating comes somehow from these vector fields and a direction of a path that you're traveling. I had a whole page of the different notations. That's just people trying to invent a notation that works for them. And I gave you an example here of how you would compute them. The only other thing to say is there's some theorems that relate these. The only one that I want you to know right at this moment is, oopsie, it's right here. In the special case where your vector field comes by taking the gradient of a scalar valued function, then when you have to integrate this particular line integral, you will discover that you don't need to know the path, and therefore you don't have to parameterize the path. Instead, all you will get will be the values of the difference between the values of this function g at the end and beginning points of your path. And it's actually very simple. I wrote out, I never make you guys do proofs, but the proof here just shows that if you take this composite function, g composed with the parameterization phi, its derivative would be exactly the thing that you're supposed to integrate in those in the formula for how to evaluate these path integrals. And if you find yourself integrating the derivative of something, you remember the fundamental theorem of calculus. If you integrate a derivative, you just get back to the original function evaluated at the two endpoints. Anyway, don't worry about the proof. This is what is sometimes called the fundamental theorem of line integrals. It only applies in the special case where your vector field is the gradient of some other thing. And then you can evaluate these integrals by just subtracting that other function at the two endpoints. For those of you with a little physics background, this applies in the case where you're trying to figure out how much work to do when you're fighting a force which is a conservative force. A conservative force is one that comes from a potential energy field. And all this formula says is that when you're fighting a conservative force like gravity, then the amount of work that you do when you follow a certain path from the point P to the point Q, the amount of work done can be calculated by simply subtracting the potential energy at the end minus the potential energy at the beginning. So if you have a little physics behind you, this so-called fundamental theorem for line integrals, it's really quite easy and natural. All right, there's a couple of other theorems that we're actually not going to get to until later, so I can just hide all of those, which means that I got through all of the slides I wanted you guys to see today. And my timing is perfect. It's exactly 11:50. But let me ask now if you have some questions about these line integrals. And again, your questions could revolve around the meaning of them, the notation, how you compute them, or the one theorem I just gave you. Everybody's really quiet. You good?
I have a question.
Go ahead, Ethan.
So with the last theorem, I think there's actually a homework question on this, but how do you verify that a function can be written like
how do you know if your vector field is one of the special ones? I have two answers for that. One is you could try to figure out what G has to be. I mean, if you think that it might be a vector field, a conservative vector field, you could actually say, let's take this one that I had earlier, x plus 2y, comma, minus x plus 3y. Oh, I should probably do that on this. That's is this one going to be equal to the gradient of some function g? Well, if it is supposed to be, then this part right here would have to be the partial derivative of g with respect to x. So that would force you to have g of x comma y be something like 1/2 of an x squared plus 2xy. And of course, you could add any function of y alone at the end, and then the derivative of this with respect to x would match that. So, hey, so far so good. This looks like it might be the gradient of g, but any such g would have to have this form. And now let's see whether or not the partial derivative of this with respect to y matches that one. Well, when you take the partial with respect to y of all this stuff that I just wrote, you'll get a 0 and a 2x. And, well, whatever the derivative of that function of y alone might be. So this would be more y's and only y's. And I could make that part match the 3y, but I can't change the fact that the 2x doesn't match the negative x. So the answer to this question is no, this one is not a conservative vector field. So that's answer number one. And you would have to pursue this line of thinking if you really did have a conservative vector field and you wanted to know what is the G. But the other thing you could do is, without all of these calculations, the other test is, in order for this really to be a gradient, you would need to know that the partial with respect to y of this one would have to match the partial with respect to x of this one. That's exactly the problem that I had here. That 2 came from that 2, but that 2 didn't match that -1. So it's these two partial derivatives that would have to match. And if you remember what we said earlier about, earlier in the semester, we talked about second order derivatives. If this guy is supposed to be the partial of g with respect to x, then this would be the mixed second order partial derivative of g with respect to x and y. And so with this, it would have to be the same thing. And this kind of leads to the other type of test for whether you have a conservative vector field, and that is, you would need to know that the curl of the vector field is equal to the 0 vector field. If that happens, so if f is equal to the gradient of g, that would imply that the curl of f would be the curl of the gradient of g, and that always comes out to be 0. So this is the other test that you could use. It's one of the theorems that we had back in the days of vector fields.
Can we see the whole paper, please?
Oh, sorry, how much of it do you see? There.
So the curl method works in general for like 3D
correct
vectors. Okay.
Correct. But when you write down what a curl is asking you to compute, just saying that the curl is supposed to be 0, it would mean that you'd have to be writing down 3 equations just like this one. Various kinds of partial derivatives would have to match. So really, this is just a very succinct way of writing the exact same thing that I wrote over here. And by the way, this should sound like the fundamental theorem of calculus, right? If you guys have already talked about the differences between the vector fields in R3, for which this might be the better way to write it, versus vector fields in R2, for which this is the better way to write it. You could also talk about vector fields in R1, and if you write all this stuff out in one-dimensional curves, you'll discover that, oh, that thing I called the fundamental theorem for line integrals, that's really just the fundamental theorem of calculus. It says that if you are trying to integrate a derivative, well, you just subtract the value of the function at the two endpoints. So it's pretty cool. It looks cool to have these theorems that make things look really easy, but on some level, it's not really as sophisticated as it sounds. Anyway, don't worry too much about these theorems, but I do want you to be ready on the exam to not get frightened by the different variations of notation. And I would like you to be able to compute a line integral, really just using the kind of steps that I used in this one example. Okay? Everybody good? All right. Give it a shot. Try to finish that homework. Turn to each other on Piazza for help. I will try to tune in as well later today. And then I'll get that email to you that you guys requested all the information. And the test itself will be available midday tomorrow sometime. All righty, guys. Good luck.